Hi, thank you for joining me in this presentation at ICUAS 2022. My name is Irvin Vasquez, and on behalf of my colleagues, I'm going to present the paper Spiral Trajectories for Building Inspection with Quadrotors. The motivation of this paper is that there are several monuments and several buildings that need to be inspected regularly in order to prevent damages. The task of inspection may be defined as to move a sensor to a set of different locations in order to observe the whole surface. Some application for this task is facilities examination, cultural heritage conservation, 3D modeling, etc. The inspection of large buildings may prevent human and material losses. For example, in the right figure, I am presenting a very famous Mexican monument named Light Trail. This monument has to be inspected regularly in order to prevent damages. To plan an inspection of a target building, we require a previous model. However, in many cases, this previous model may be unavailable or it may be incomplete. Some solutions to this problem can be to model by hand the building or to perform a 3D reconstruction using depth sensors. However, the modeling by hand could be an expensive task, and on the other hand, 3D reconstruction with depth sensors could be a difficult task because we require expensive sensors and experts in the field of 3D reconstruction. An alternative to these 3D complete models, we can use 2.5 dimensions models. These models are good approximations and are easier to be obtained. By definition, these 2.5D models only contain the altitude for a given point in the surface or in the floor. So we can construct the buildings as in the right figure. These models are easier to be obtained because with a photogrammetry flight we can obtain this kind of shape. A limitation, of course, is that we cannot represent holes in the building, but this is a first approximation. So for the rest of the paper, we assume that we have a rough 2.5D representation for the target building. Then our problem is to compute a trajectory for a quadrotor so that the whole surface of this representation will be completely observed. In particular, we are focusing on computing smooth trajectories for the quadrotor. There is some information that has to be included in this method. First, we are assuming that the drone has a frontal camera that is observing to the building. This camera should have a gimbal to compensate the pitch and yaw movements of the drone. A well-known example of this configuration is the Parrot Bebop drone. In addition, we know the building height, and we also know the distance between the building and the camera. Usually this distance is specified by the spatial resolution that we want to achieve and the sensor in the camera. With this information, we pretend to compute these trajectories that goes around the building and observe a stripe of the building, like painting the building. So after each trajectory or after each spiral, the drone increases its altitude by delta H. And this delta H can be computed by defining the overlap that we want between stripes of observation. So in the right figure, I am presenting a graphical description of the task where the drone is moving around the building. Here we can see the method's general overview. We start with the 2.5D model, and this model may be in several formats, so we convert this model into a voxel map. Once we have the voxel map, we have to select several slices at different altitudes. This is done because usually the voxel map resolution will be higher than the number of laps around the building to complete the observation. So we are selecting the several slices depending on the delta H that we have computed early. So we have a number of slices, and for each of these slices we are going to compute a target ring path. So once we have the slices, we compute a contour for each slice, and then we convert this contour to a target ring path. Once we have all the paths for completely observe the building, we map each of these paths that are in the workspace, we convert them to the frequency space. And this is done because we want smooth trajectories. So in the frequency space, we can select those frequencies that are smooth but also follow the target path. Then we use the inverse Fourier transform in order to get the workspace path from the selected frequencies. So now I'm going to dig into the details of each step. So assuming that we have already computed the slices for the voxel map, we apply this algorithm that converts the slices into discrete signals for each of the components of the path. So we start with the slices, and then we delete all these slices by a kernel that is specified according to the distance from the camera to the building. Once we have deleted the slices, we compute the contour of them. In some cases, we can get more than one contour, so we only keep the largest contour as the path that the drone has to follow. So in the next step, we return from the voxel map representation to a workspace representation where we defined the scale according to the real space. After this algorithm, we have a set of discrete signals for each component of the path. Here is an example of the process. We have the target building, and for this target building we compute a voxel map that it is not presented here. However, for this voxel map we compute several slices. Here we can see an example of one slice. There are several ones to complete all the altitude. So with this slice we compute a target path that is the contour of the dilated slice, as we can see in the right figure with the target path. Then we split this target path into the X component and the Y component. Here we can see the X component and the Y component. In this case, we are mapping from the workspace to a time space because this trajectory has to be followed in a determined time. As we can see, each of these components resembles to a one-dimension signal. So these signals will be mapped to the frequency domain in the next step. Here we map all those signals to the frequency domain using the Fourier transform. In specific, in our implementation, we are using the fast Fourier transform. So using the transform, we can obtain several components, each component related to a frequency. The combination of those frequencies can reproduce the original signal. So, a filtering of signals can be applied in order to smooth the trajectory. Once we have selected the components, we return the frequencies to the workspace domain or to the time domain using the inverse Fourier transform. And this is mainly the proposed method. So we have tested our method in a simulation. First, we compare the fitting performance of the Fourier transform versus a polynomial fitting. We have used three target shapes defined by a set of vertices. So we compare how those fitting methods can approximate the target path. Here in this figure, you can see the three shapes that we have selected for experimentation: a square, a trapeze, and a figure that resembles a bat. In the upper figures, we can see the 2D representations, and in the bottom figures, we can see the paths that have to be followed by the drone. So we tested the proposed Fourier transform and the polynomial fitting for several components, and here in the upper figures we can see how the Fourier transform is fitting to the target paths for one dimension. And in the bottom figures you can see the combination of the frequencies to reproduce or to approximate the target path. As we can see, the reproduced paths are quite similar to the target. To measure the performance of the fitting, we have computed the mean square error for each tested approach. So here we have the inverse Fourier transform and also the polynomial fitting. In the columns we can see the error for each figure. As we can see, both methods can approximate the figure. However, as we increase the number of frequencies, we can see that the path is approximated in a better way. So the best approximation is obtained by 100 turns of frequencies. To test the method, we have implemented a PDI cascade controller. So to observe the trajectory, I'm going to show you a video. So in conclusion, we have presented a method for computing paths that cover the target building, and these paths are initialized in the workspace, but they are mapped to the frequency domain by using the Fourier transform. The idea is that we can select some frequencies in order to smooth the trajectory. According to our experiments, the paths computed with the Fourier transform are closer to the target paths with respect to the paths computed by polynomial fitting. In a future work, we will compute the missing yaw angle, and we also apply this path to real inspections. Thank you for watching this presentation. I will be happy to respond to your questions, and if you require more details, feel free to read our paper, or also you can write me a mail. Thank you.